Be honest with you, Justin, I never know quite when that segue music is dying down to let us go or starting all over again. Much like the methylation cycle, by the way. And that's the topic of this evening. Methylation. It's a complicated topic, though, right, brother? I mean, this is something we deal with our clients day in and day out. It's important, if not one of the most important pathways that we study at the DNA company.
Yeah, it's incredibly important, and it's sort of invisible to us. You know, what's going on behind the scenes at all times. And it's a really relevant process because all of your DNA needs to be methylated in order to work. You know, so
Right.
knowing if you're like a hyper or a hypo methylator has so much trickle down effect for human health that it's unreal. And that's why the DNA company, we've tried to simplify this overwhelmingly complicated process and really whittle it down to what matters and the efficiency of the cycle. So we'll talk a lot about that tonight because it relates to things like chronic disease wholeheartedly, because it's about
Absolutely.
how your cells function and how you deal with things like inflammation.
And you and I both taken courses in complicated molecular biochemistry. We're not asking anyone who otherwise isn't a clinician here to be an overnight molecular biochemist. But we do appreciate the complexity. And one of the things we do really well at the DNA company is simplify the process. You know, it's a chemical. We can't get away from the fact that it's a chemical process. So I don't care. We do care. We have empathy. But at the end of the day, we can't care too much about how you hated 11th grade or 12th grade biology. In some respects, this goes a little beyond that. But this biochemical process that happens billions of times every second in our bodies, and as you alluded to, kind of like adding little tags or on and off switches called methyl groups to a whole bunch of key molecules, helping genes turn on and off, process toxins, produce energy. Things don't work in your body unless methylation is happening. Supporting mental health, a huge one. Inflammation. I mean, it's synonymous when it's not working properly with inflammation, hence chronic disease, and that's of course what we're going to get into in a deep way this evening. But you know, due to genetic factors and variations, by the way, it drives me nuts. I don't know about you. There's a bunch of companies out there and people out there, bloggers, podcasters, and all these people that are using the wrong vernacular. Maybe we start there. This is not about gene mutations. If you spell the word center, center, it means the middle of somewhere. If you spell it centre, maybe you're in the US and you're spelling it in American fashion. It still means in the middle of somewhere, but if you spell center TCN, RE, it means nothing. That's a mutation. We're not talking about methylation mutations. You'd have serious problems. We're talking about variations within your methylation capabilities, and it's nuanced. So, our bodies can become more prone to inflammation, which is at the root of many chronic diseases. Bottom line, from heart disease to cancer to mental illness issues, and even autoimmune conditions, obviously. So today, bottom line, right, Justin, agree with me or not, we're going to explore the genes involved, like MTHFR. You can use that acronym however you like. COMT, COMT, MTR, MTRR, SHMT1. You can throw a whole bunch of acronyms around and make it simple. We're going to learn how understanding and supporting our unique methylation process and our unique tools, and then of course the powerful tools that we can use to offset whatever genetic aptitude we have to prevent and manage chronic disease. Right? That's the point.
That is the point, and it's really important to note here that this is an ancient encoded process. However, the epigenetic expression that we now live through, it's the lens of 2024.
Right.
Right? Because we know that our ancestors, unless they lived next to an active volcano, didn't have the problems with, let's say, pollution as we do now, right? So there's all these factors like that that have influenced the methylation pathway negatively to where we're methylating things less efficiently than we used to. But that's when it was created, right?
Right.
Human evolution was this crucible that landed us with all these different genes and genotypes, but we're living in this modern world now, right? So our methylation, we have to dial it in even more than ever because it's more important. There's more things working against us.
Right. so many thousands, hundreds of thousands of years ago, right? Our ancestors roamed the earth, widely different environments. We're not going to get into the world of anthropological, history and theory here, but we came from different parts of the planet. Primarily, theory goes Southern Africa and Africa, eating diets that were, wildly different. Some filled with fresh, unprocessed foods, obviously, very rich in essential nutrients. But whether or not we're hunting mammoths in the tundra, right, or gathering berries in lush forests, or maybe we're fishing off the eastern seaboard and rugged coastlines, humans adapted to survive based on the food, the climate, the terrain, the threats that were all around them. So, bottom line, though, back then, our bodies didn't have to work overtime to get nutrients like folate and B12. By the way, they're the heroes of tonight. Okay. Folic acid, B12 in their right forms are the heroes. And we're going to talk about this in a big way. They're not the solution and end all and, of all chronic disease, but they're very important in this process. And when we serve them or they serve us properly, a lot gets better. So anyways, we were picking these up, from nutrient dense diets that were the norm back then, right? There's nothing other than highly micronutrient dense foods. So, some of us developed gene variations that worked perfectly fine in those conditions, like, for example, slow versions of certain methylation genes. They were perfectly natural and they were fine. So, some of these variants helped us to conserve energy, right? Stay alert for predators, even survive through long, not droughts, food less winters, when food was scarce. So fast forward to today, like you were talking about, the modern lives we live now, completely different. Right? We're juggling processed foods, micronutrient deficient foods, high stress work days, a lot of pollutants our bodies hasn't seen before, synthetic chemicals, all while sitting at our desks, which we're guilty of right this second, scrolling through screens and rarely touching nature. So our bodies haven't evolved. They haven't completely caught up. And we're carrying around gene variants from a world where basically food was this, unprocessed, toxins were minimal, and stress was about survival. By the way, that also plays a role in COMT, a gene we'll get to momentarily. So here we are in 2024. Genes that served us beautifully in ancient settings are now trying to keep us, caught up in this fast-paced, nutrient-depleted, stress-loaded world. And that's the history behind it. Sometimes, to your point, genes, they stick around in order to create variety within populations that in the chances it becomes survivalistic or optimal later on down the road, they're sort of there within the population to pop up again. So I'll give a perfect example, and then you'll talk about COMT, slower functioning MTHFR, right? The methyl tetrahydrofolate, methylene tetrahydrofolate reductase might now make us more vulnerable to things like fatigue or cardiovascular challenges. But then, for example, what I was alluding to, adaptations to ancient environments, right? Slower methylation in some populations might have helped conserve resources in these low calorie environments or during times of fast and famine. But why don't you go ahead and describe COMT and how in those days of, chances of getting eaten by some predator, it was survivalistic to be, that sort of, brooder or what's the word I'm looking for? Help me out here. Hamster wheel, right?
Yeah. Yeah. Well, and, an important note here is that the goal of methylation here is not to upregulate everything. We don't want each and every gene working in its fastest possible capacity. I think that's where a lot of the problems can come in some of these a little bit more basic gene tests and things, because there's certain genes associated with inflammation, right? There's things that promote inflammation, promote tumor growth. We don't want all of these things to be upregulated and overmethylated. So that's where the nuances come in. With regard to COMT, it's interesting in modern context because COMT really has a big role in methylating different neurotransmitters, right? COMT is catechol-methyltransferase. Start breaking down the names of these genes, you'll start to understand more about what they do. And among its primary roles is methylating things like dopamine and methylating things like noradrenaline. In 2024, that is a very different picture that we're looking at than it would have been for our ancestors, because your brain doesn't know the difference between a perceived threat and a real threat. It also doesn't know the difference between a positive reward and maybe a negative pleasure-based activity, right? Your brain gets dopamine from things that are good for you as well as things that are bad for you. And your brain also freaks out and you get this release of adrenaline from someone cutting you off in traffic or seeing an inflammatory news article. But our ancestors, that mechanism was actually made for an actual predator jumping out of the woods at you. Right. So it's an overstimulated pathway now. COMT is interesting because it operates at different like speeds, right? So it methylates the neurochemical. It just, all I mean by that in this case is it makes it available to be taken up by the receptor site, but then it clears it after as well. And the speed of the enzyme is going to matter because you can have really quick clearance, right? So it goes away super quickly, or you can have kind of a moderate clearance, which is good. You get a little bit more of a Zen type of a profile, or a longer clearance, right? So let's say if we're talking about noradrenaline and the COMT enzyme is clearing it super duper slow. Well, that feeling of panic that really you would hope to only last a little bit to get you out of the situation, it's going to be prolonged, right? And that's where we see, post-traumatic stress. That's where we see these anxiety disorders. It just doesn't go away quick enough.
Yep.
COMT also methylates things like toxic estrogen metabolites, like 4-hydroxyestrogen as well. If 4-OH were to stick around in the system for too long, it can cause problems, inflammation and DNA damage, etc. We'll talk a little bit about DNA damage, I'm sure, tonight, because methylation is important for that. But that's what I mean. The speed of that enzyme can cause more hormone toxicity. It can cause more anxiety, binging, properties, addiction properties. So COMT in and of itself plays many roles in the body.
Yeah. And perfectly said, and sort of speaks a little bit to the trade-offs in biochemical pathways I was describing evolutionarily. So this energy conservation, high efficiency, and that's what you're talking about. Some, hundreds of thousands of years ago, high efficiency methylation genes, they require more energy. They require more nutrients. They, they could be disadvantageous when resources are scarce. So in our historic evolutionary sort of limited environments, people that carried reduced methylation efficiency could actually conserve energy better. That's why this, in one argument, some of these poor variations continue to persist, not just to add variety to the population, but because at one point it was survivalistic. And so to the MTHFR point, to the COMT, the COMT point, particularly, by the way, as it relates to COMT, the impact on neurotransmitters, which you eloquently described, certain methylation variants impact that degradation or recycling and uncoupling of neurotransmitters, which influence mood and behavior, and particularly the stress pathway. So, for example, slower COMT, that leads to higher dopamine levels, higher catecholamine levels, right? Which also, by the way, can enhance focus and alertness and concentration. So in certain contexts, bottom line, we can get off the evolutionary tip. High stress, high threat environments, this heightened state could be, and frankly, likely was advantageous, but no longer is, because, my friend, this is not a tiger, right? But we treat it like it is. So we're going to get into that, and obviously how that contributes to chronic disease, how we interpret the neurotransmitter pathway. But most importantly, some of the genes, just to park for a minute: MTHFR, SHMT1, MTR, MTRR, and then this sort of side show, if you will, of fucal transferase and how important that is. We're going to put it all together, going to make it really simple, and then how it all relates back to chronic disease. But methylation, as you put it earlier too, affects gene expression. I just want to quickly sort of really distinguish, if you could start, the difference between, DNA becoming methylated and the DNA we actually look at and test that describes your methylation pathway. I think it's really important to start there.
Yeah, and it's funny. It's kind of a chicken or the egg thing, because there's genes that actually influence this pathway. Genes encode enzymes, remember, and enzymes are what do a lot of these processes. So we have genes that steer the boat when it comes to how the methylation process works. A number of them, Dr. Wylde just mentioned. Then once we have the process, the baseline process, that process is what methylates all the rest of your DNA, right? So you can over or under methylate, and that can cause differences in gene expression, right? So the genes that do the job would be the 5 that you described. You've also got COMT in there. So we test for several genes. It's actually a big pathway. So we look at MTHFR, for which there's 2 SNPs that we look at, SHMT1, MTR, MTRR, and then we added a sneaky one in there called FUT2, fucosyl-transferase, that Bryce just mentioned. So those are the pathway. That's what actually does the methylating of all the rest of the genes, your estrogens, genes associated with neurotransmitters, anti-inflammatory genes. All of these things have to be methylated in order to do their job. So there's genes that do that, and then there's genes that get methylated after to do their job. So genes are really encoding a ton of this process. It's very complicated, but that's why we've dialed it in to this relay race analogy that we use. We look at these genes and we look at the efficiency of the cycle, because if we were to isolate one gene, like MTHFR, for example, MTHFR can do its job in a suboptimal manner, and your body can still have an overall efficient methylation cycle. We have to look at the totality of it, because it just goes around and around. Your body is always doing it thousands of times per second. So we know where to place interventions based on how these 5 baseline genes work with different nutritive substrates, etc. But that's the difference. There's ones that are the chicken and there's ones that are the egg.
Right. Speaking of chicken and egg, chronic disease link. Chronic inflammation can alter methylation. Poor methylation can cause chronic inflammation. So methylation is highly responsive to lifestyle factors that interplay with your genetic aptitude and predisposition: diet, stress, lifestyle, or rather sleep, exercise. And so obviously by understanding your genetic aptitude and then optimizing these factors, it's actually possible to positively influence methylation patterns. It's possible to encode for less methylated DNA. It's possible epigenetically to favor less of a hypermethylated state. Homocysteine being one of the star actors of this, maybe bad actors of this play. Reduced methylation is maybe the better actor, but high homocysteine levels, and that's a surrogate we can talk about as well, signal methylation imbalance and inflammation. So cool fact, actually, homocysteine is a natural byproduct of methylation. It's sort of the end product that turns into, or we hope in the right context, turns into S-adenyl methionine. But high homocysteine is a warning signal that methylation isn't working efficiently, right? So the chronic disease link there is that elevated homocysteine is associated with that chronic inflammation we talked about, heart disease, cognitive decline, Alzheimer's, degenerative conditions, you name it, anything with an itis really at the end of it, right? So before we get into that long laundry list of, crazy amounts of chronic disease and maybe what we can do about them, why don't we drive this home as an analogy to a relay race? This is what we look at the DNA company in terms of sort of a stepwise process. We're going to really simplify this and bring this home. You just described it. It was great. But let's talk about first, second, sort of that third runner being fucosyl-transferase, and then fourth, and then of course your anchor, right? So SHMT1, that kicks off the race. Now, if this is a relay race and the runners are the enzymes you described, right, in this DNA analogy, and the baton is the biochemical or the molecular CH3 group, that's a methyl group. And of course, finishing that race without dropping the baton in order to qualify, that is creating that methyl group donation, right, to be able to pass on. That's the complete race, to your point, happening thousands, millions of times a second in every cell. First runner, serine hydroxymethyltransferase 1, SHMT1. That kicks off the race, right? Boom, out of the start gates. It prepares folate by converting it into a form that ultimately can be further processed down the line. So this is really where it starts. If your SHMT1 drops the baton in the handoff, let's call that the A allele variant. struggle to get that baton moving as quickly, drops it, trips itself, whatever. For those folks, folinic acid as an alternate form to folate can actually be a booster here. Whereas, to your point earlier, throwing all kinds of other methyl groups, like arming that first racer with 5 batons, it's not the solution. But let's park that solution, sort of what we do about it, the folinic acid, come back to that. The second runner, right, where SHMT1 hands off to MTHFR. Tell us about that runner.
Yeah, so MTHFR, it creates 5-methyl tetrahydrofolate, right? A lot of this process is just about adding methyl groups and getting to the end, which is your body having enough methionine and a proper ratio of methionine to homocysteine. To Bryce's point, that's a good metric to keep your eyes on. If your homocysteine is always elevated, that's just an indicator that the methylation cycle is not going well, right? So MTHFR, I mean, we evaluate the 2 SNPs. There's the 1133 and the 1131. I think that's the one. And the efficiency of that passes the baton on to the next one. If you can't make enough 5-MTHF, then the baton has fully been dropped at that point, right? So it matters that your body can actually do that. MTHFR does that. It creates 5-MTHF, and then that passes it along to the next runner.
Right. So not a classic runner. I mean, most relay races have 4 runners in them, right? We're putting a 5th in here. We call this fucosyltransferase, a fucosyltransferase 2, FUT2, FUT2. This takes the baton, although not really, I don't know, a racer. This analogy has this ghost runner in it. Okay. So fucosyltransferase is very important because although its role isn't sort of like directly in methylation, this is where the DNA company, among other genes we look at, is better than any other company out there. Not only do we simplify methylation, we really look at the most important gene variations that control the whole race. So anyway, fucosyltransferase FAT2 variations, particularly in non-secretors, they're called. People that in their gut lining don't have the optimal variation of this gene to allow for absorption of B12 through the diet. Keep in mind, evolutionarily, this is animal protein, things we get from animal-based foods, doesn't come, from a vegan diet, but also the genes that control for one's ability to absorb from their gut is all managed by this fucosyltransferase gene. So imagine, this is where we're going to get simple. Fucosyltransferase, FUT2, carrying not just the baton, but also a toolkit for B12. So without enough B12, think about it like this: the later runners, they struggle to keep the baton moving efficiently. So this B12 is a sort of an indirect intermediate ghost runner handoff. So we'll come back to the supplement solutions momentarily, and how we manage certain variations of B12 given your genetic aptitude. The 4th runner is MTRR. Tell us about MTRR.
Yes, so MTRR, now we're on to methionine synthase reductase, right? Again, start analyzing the names of these genes because it starts to make more sense when you realize what they do. So MTRR plays a role in the remethylation of B12 into methyl B12, right? So it's adding that methyl group. MTRR does that. So, if you don't have proper MTRR function, you can end up with reduced overall bioavailable levels of B12 as well. So you need to know what your genotypes are for this. This completely pairs with that FUT2 gene, fucosyltransferase, because a lot of people based on that genotype can't actually get B12 through the gut barrier.
It's got to be there in the first place for this guy to even work, right? At the end of the day.
So without it, that's why we look at that gene. It's not a methylation gene, to Bryce's point, but B12 cobalamin is so friggin' important to how this cycle works and the efficiency of it. We need to know your capacity to actually get it from food and get it through the gut barrier, right? So FUT2 is like a taxi cab that takes it through the gut barrier. If you're totally suboptimal there, that is going to make it so that you can't get high enough levels of B12 to where supplementing now is going to be either, sublingual or intravenous. But that's what MTRR does. It remethylates B12 into methyl B12.
Exactly. So with a G allele, we'll come back to these sort of the solutions, the stop gaps to make sure this race is run efficiently, the fastest possible, and handing off the baton without dropping it or fumbling it. To summarize, if MTRR at this stage, fourth runner, but really the third with the ghost runner involved, has a G allele, may not be as efficient at the task, right? So with a little bit of extra support, we'll talk about that, methylated B12 and or a form of what we call adenosylcobalamin, MTRR might sort of proverbially keep up the pace, if you will, right? Ensuring that homocysteine doesn't pile up. That's the whole point. Lastly, the anchor, so to speak, some people might call the MTHFR the anchor. It's really not. It's where things, there's the stopgap there. People, a lot of companies out there make this mistake. They don't consider methionine synthase. That's MTR. So, and of course, it doesn't end here either. We acknowledge that, folks, but this is getting the whole thing going. And if it doesn't happen here in the first place, it's terrible downstream. MTR in a last stage of a sort of anchor in the analogy of the relay race takes the baton to the finish line, and it uses the methyl B12 from MTRR, which only gets there because of fecal transferase, to convert homocysteine to methionine, and then methionine, of course, to S-adenosyl methionine, and then the stages are somewhat complete into the handoff of the CH3 group to give to molecules, like to give to the enzyme COMT in order to, uncouple the catecholamines, for example, or to take that nasty 4-OHAE that you were talking about, 4-hydroxyestrogen, and detoxify. So if MTR has a variant that's suboptimal, it slows down the last leg of the race. You don't win. So that leads to elevated homocysteine levels, right? And potentially health risks, which are often chronic. So with a smooth handoff all the way through, starting with SHMT1 over to MTHFR, fecal transferase got to be there to deliver the B12, MTRR into MTR. This whole pathway is then satisfied. And hopefully that drives it home in a as simple as possible manner. And again, we're acknowledging it doesn't end there. Now, I want to also once again drive home the methylation pathway as we described it, right? Versus we also test for aging, right? Calendar versus chronological, rather calendar chronological versus biological aging, right? The way we do that, most biological aging clocks, methyl clocks do this, is by looking at multiple CpG site methylation, right? So a specific type of methylation that happens directly on DNA. This is different. So methylation of DNA affecting epigenetics and accentuating aging and even contributing to chronic disease is different than the methylation cycle and how well we do that, as we just described, right?
Yeah, it's part of what we look at as far as the chronological versus biological conversation, because epigenetics and managing that is like 90% of the actual end health outcome, right? So it's, we use this analogy, we've talked about it recently about how, genetics load the gun, lifestyle pulls the trigger. That's the difference. It's an upstream versus a downstream thing. How is it actually methylating and manifesting? But this is the baseline encoding process. And as we said at the beginning of the call, this encoding process is hundreds of thousands of years old. But now here we are with all of these additional disruptive elements. Something as simple as someone who smokes cigarettes, for example, that really puts a wrench in the entire methylation cycle, right? And there's so many things. Wi-Fi and pollution and mold is a huge one for disrupting this process. So the end, how your cells are aging, is going to be accelerated based on that, right? So that's what we look at. The actual clocks themselves matter because we want to see how your cells are aging in response to epigenetics.
Exactly. Okay, well, I think we did that in a respectable way. I'm very happy with that. Why don't we? I've lost it. I'm looking all over my screen here for the poll this evening. Maybe we could punch that back up. There we go. Thank
There
you.
we
We
go.
have some like geniuses in the back end controlling all of our bells and whistles here. So we're asking you guys tonight. Hopefully, most of you filled it out this evening. We're incredibly receptive to questions of any sort. Please put them in the Q&A. Looks like we're loading up there already. We'll get to all those. But in the poll, We asked about methylation and its role in chronic disease and how familiar individuals joining us this evening are with the concept of methylation, its impact on health. And we asked very familiar versus somewhat versus, yeah, I heard of it, but not too much. And this is entirely new to me. It's a bell curve. Somewhat familiar took the poll at 55%. And I would say that makes sense. A lot of podcasts out there, a lot of people talking about methylation. It's everything from kind of cutesy, throw a, $800 test at you and a plethora of vitamins and hope you do better, all the way through to, some real cool advanced biochemical, individuals who know what they're talking about. But all of it's complicated. And so that's where the somewhat familiar comes from. We at the DNA company, we're making it simple. We're reinventing it as simplified because it is a very biochemically complicated pathway. So some have said, I've heard of it, but don't know much. That's the majority of the group. So we want to simplify it for you. We'll reiterate any of what we just described as many times as we have to for you to get it. So we'll go through the poll, and before we start taking questions, of course, we'll talk a little bit more about some chronic disease related to this, and also how to solve the gaps in those pathways that we talked about with some really simple varieties of B12 and folate. The second question we asked was, what health concerns are you most interested in understanding in relation to methylation? It's a total split. General wellness wins this, but cardiovascular health is up there, cancer, mental health, it's evenly split. So we're going to talk about it all. Third question we asked was, have you ever heard of genetic testing done to understand your methylation related health markers? And yes, by and large, one. So I'm glad people have heard of it. Whether they know how to interpret it's another question. 17% said no, and about 6% say they're considering it. Lastly, we asked, which factor do you believe has the biggest impact on methylation in your life? Relatively split. People are calling out diet. Stress is at 13%. Environmental toxins are at 27%, and genetic predispositions at 37%. You know what? I think that's a pretty accurate split for real life. What do you think? I mean, maybe genetic predisposition should be a little higher. That's probably somewhere closer to 45%, maybe 50%, but certainly diet, stress, and environmental toxins plays a huge role in all that, right?
Yeah, well, and it's, the term environmental factors or environmental stressors, it means a lot of things. That's a fairly broad umbrella. I mean, you could argue that diet is an environmental factor, right? As far as the
Right.
environment being all of our input, the things that we're putting into our bodies via the respiratory tract, the digestive tract, just visually, the limbic system, whatever that input looks like. I think all of it does have some trickle down effect to the methylation process as well. So it makes sense.
Absolutely. So, in the three areas people are interested in hearing about, cardiovascular health, cancer risk, mental health, we could extend methylation to so many other things. Methylation is kind of like, I don't know, a health inspector for the cardiovascular system, keeps a really close, tight watch on, homocysteine, which again, if that's not in check, it builds up into the intracellular spaces within each of your cells, the billion, trillions of cells you're made up of, and causes inflammation. And that's a medical buzz term of the day for a good reason. It's the underpinning of all things that cause chronic disease. So, homocysteine is just one end product, but it is like an alarm bell. It does signal increased risk of artery damage. And of course, cholesterol is the old, news. Particle size counts, ApoB, LP little a, but inflammation warrants the deposition of cholesterol in the first place. So, nitric oxide plays a role. You can unpack that if you like. But when methylation is on point, your heart and your blood vessels, and there's some other genes we look at, 9p21 being one of them, and detox pathways, they all interrelate here. But when methylation's on point, your heart and blood vessels get the tender, loving care they need, especially when other genes are at risk. Believe it or not, we have like almost 50 questions. We're going to get to them real soon. but cancer risk. Do you want to unpack that real quick? I mean, the methylation and DNA repair, when it's not properly repaired, cancer is what? It's like rogue cells with improper, instruction that just go haywire. Methylation is a major underpinning there too, right?
It is because, it's like I said earlier in the call, we don't want to just have this baseline concept in our minds that we want to just turn on as many genes as possible and that we want to just upregulate gene expression to the best of our ability. So many of our foods are fortified with folic acid. We end up with way too many, B vitamins and different things that are actually upregulating the whole process. When it comes to things like cardiovascular health, listen, there's genes associated with glucose metabolism, lipid metabolism, the regulation of different inflammatory processes in the body. So when we just overmethylate or hypermethylate, you can turn things on that you don't want, pro-inflammatory genes. I think the same conversation is really relevant for cancer. If we're creating an environment that is favorable to abnormal cells, right? Like abnormal cell activity, a cancer cell is a normal cell that has a wonky metabolism, right? So it operates on the same principles of life. We don't want to nourish it and cause it to grow. Certain gene
Or
expression
divide.
can do that, or divide, multiply, replicate. That's a bad thing in certain circumstances. In other circumstances, replication and division are good, right? So understanding that methylation has a trickle-down effect of all sorts of DNA regulation. We don't want to willy-nilly up or down regulate. That's why we have to have the cycle on point. A balanced methylation cycle won't do either of the above. You won't be hyper and adding too many methyl groups, nor will you be hypo and having an unfavorable methyl group to folate ratio in your body. It's a really important ratio because genes can do bad things as well.
Right. So when methylation is working effectively, it's kind of like a repair crew in your DNA, right? Where that light switch, however you want to look at it, constantly scanning for broken DNA, patching it up before it becomes a problem. But if methylation gets all messed up, it may miss those repairs. Got a drunken worker on staff, and just goes over it, patchworks it, whatever, and that leads to uncontrolled cell growth, tumor development. In other words, methylation in that balance you described acts as like a quality control team, right, for the trillions of cells in the DNA that controls the cell turnover. And that's sort of how it works as it relates to reducing cancer risk. And then there's the mood factors. That's cardiovascular disease, inflammation, cancer. Then there's neurotransmitters and the biochemistry that controls mood, executive function, behavior, attention, alertness, sleep wake cycles. So mental health at large. It plays a key role in producing dopamine, right? Serotonin, noradrenaline, adrenaline, all these things that regulate mood and behavior. So, what's the word I'm looking for? Not a bartender, mixologist. You can think of your brain kind of like your methylation as sort of your brain's mixologist. That's what I was reaching for. So keeping that sort of perfect balance between these mood boosting chemicals. So if it's sluggish or inefficient, or it's missing too much of this or that, throws off the balance. That's, I guess, the main point. Things hanging around too long and not being methylated to uncouple, or not long enough. Those are all the virtues of, there's no right or wrong in DNA. They are what you have. And we can up or down regulate them. You can't change your DNA, but you can manage genetic expression. And that's the bottom line. That's what we're all about at the DNA company. So before we get into the question and answers, let's just reiterate this again, right? The genetic pathway that we look at it in a simplified way, and we use this analogy of a relay race. And the race starts with SHMT1. That gene right there is so important. A lot of companies, a lot of genetic analyses out there don't account for this. But I'll tell you, if that gene is suboptimal and it's not really getting, this is what a lot of test companies fail to understand. It's not sort of that full methylation pathway is not functioning. That relay race, that the baton is being dropped right there. That's when these methyl groups, the CH3s, accumulate outside of the nucleus within the cell. And a lot of that accumulation, without being passed on, can become inflammatory. I would argue that almost all of these chronic diseases, which have an underpinning of inflammation, is as a result of that racer dropping the baton out of the gate. Would you agree?
I would agree. Yeah. I mean, you can very easily overload the cytoplasm with methyl groups, and you can also undersupport it with methyl groups. And that's why you have to know what your DNA is. And, interestingly, as it relates to what you just talked about, neurotransmitters, imagine if you're over methylating neurotransmitters, how that's going to impact your mood and behavior, right? Like
Right.
you guys have way too many of them. That's going to lend itself to, panic disorders, insomnia. I saw that in the comments. Someone asked about insomnia when it comes to neurotransmitters. I would say that over methylating could certainly have a trickle down effect that relates to that. Under methylating would be probably the opposite, right? You don't have enough to work with, and your brain is going to be always starving for them. And that's when we see depressive tendencies, brain fog, etc.
Probably the more important issue. I'm just pointing out what a lot of other companies don't do at all, which is identify the hypermethylation component. Like you said so beautifully, it's all about balance. But just before starting to answer these questions, here's the secret sauce is when we identify suboptimal variants within SHMT1, and then later in that race, the anchor, MTR, just give it away. Tell people, and then they're going to want to know if they haven't done our DNA 360, which of these variants they have. But the racer that starts SHMT1, if they drop the baton, what do we do? And then making sure that this race is complete. What do we do if MTR is not bringing it through the end finish line?
Yeah, so this speaks to whether or not you need to, on purpose, add a methyl group to your supplementation. I'm not a big fan of these pre-methylated formulas that every B vitamin has a methyl group added to it, because once again, you can easily over-methylate that way. The way that the SHMT1 gene and the MTR gene are going to work is that folate can either be methylated or not. If you have I believe it's the G allele in the MTR gene, that would mean that you actually want to reduce the methyl group and go ahead and use a folinic acid. I'm not a fan of folic acid. As I mentioned earlier in the call, it's really used to fortify a lot of carbohydrates and things, and we can be oversaturated with folic acid. There's a toxicity limit there. So folinic is the one that we prefer. But if you have that allele in SHMT1, you're going to need to actually not overmethylate in that circumstance. You're going to want the folinic acid as opposed to methylfolate, right? If you're AA, then go ahead and use the methyl. With MTR, that's when we're talking about cobalamin, right? And cobalamin is B12. So that you can use a methyl B12 or you can use an adenosyl B12. I'm not a fan of cyanocobalamin. I think a lot of us can agree that there's some toxicity present on that type of B12, and it still doesn't have the methyl group, but it's toxic where they get it from effectively. So adenosyl is what we recommend. So if you need the methyl group, methylcobalamin. If you don't need the methyl group based on that MTR gene, then you would go ahead and use an adenosyl B12, adenosyl cobalamin.
There you have it. That's the secret sauce. We have a question from an anonymous attendee who's asking, what tests do you recommend to be sure women are methylating bioidentical hormone replacement therapies? That's a big question. Obviously, we look at more than the methylation pathway. We're looking at the whole steroidogenesis pathway, steroidal hormones, how testosterone turns into estrogen, which ultimately downstream will metabolize into 2,4,16, and then COMT, as we alluded to earlier, catechol-methyltransferase plays a huge role along with glutathionization to detoxify these metabolites. I love, in my own clinical practice, the Dutch test, which is known as the dried urine test for comprehensive hormones. That's what the acronym stands for. So this is like a nice, once you have to know your DNA first, right? You have to know your methylation pathways. You have to know your COMT. You have to know your hormone pathways. But this looks at the same thing, almost like superimposed on our DNA test: estrogen, progesterone, testosterone, cortisol, metabolites, and essentially how estrogen is metabolized. And that's key, through the pathways that rely on methylation, like 2,4,16 pathways. So too much of the 4, there's a lot of solution to convert or help to, metabolize and or excrete, make more water soluble, push out of the system and shift over to 2. So looking at these urinary metabolites, I think, is a really good predictor live time, real time, as it relates to what your DNA already encodes for. Anything to add to that, Justin?
Yeah, I mean that would be a circumstance where I would recommend coaching, just because even the term BHRT, right? I mean, there's different interventions that you can jump on, and I would want to know the whole steroidogenesis pathway. Like, what does your UGT genes look like, right? How do you clear these kinds of things? What is your propensity for 16 alpha hydroxyestrogen, 2 hydroxyestrogen? Knowing the whole pathway is useful, but with regard to testing, yeah, I think Dutch is probably the standard there that you would go towards.
Okay. Jennifer's asking what specifically in the genetics makes the DNA company recommend folinic acid over methylfolate, which is a methylated form, when somebody has MTHFR variants. What's the pros and cons of the two forms? So let's reiterate. So we talked about it. People can re-listen to some of the recording, but explain it again for Jennifer who may not have heard it.
Yeah, so if you don't require the methyl group and you add the methyl group, you can now over methylate, and it's like an overcompensatory thing there. So you don't want to overload the cytoplasm with methyl groups because it can cause some cellular havoc. You can actually end up causing downstream issues there. So if on your report it recommends folinic acid, that means that due to your variants, you don't want the support of the methyl group in that circumstance. You actually want to avoid it, because you will over methylate if you're not careful. SAMe is another thing that we talk about in that vein because it's a donator of methyl groups. And a lot of people use it as a baseline solution for a lot of things. And I do think there's serious efficacy to using SAMe. I don't know if you agree on that, Bryce,
I
but
do.
it's not for everybody either, because if you're
No,
already an over methylator, we need to be aware.
I think there's, yeah, I think there's some, and again, always speak to your doctor, healthcare practitioner, pharmacist before starting anything. This is not intended to act as a prescriptive or replacement to your doctor or primary healthcare physician's recommendations. It's only for educational purposes. Having said all that, I think there's some warnings, some flags, some diagnoses, a lot of which sort of sits in the DSM criteria, things like bipolar, maybe schizophrenia, that by adding, and again, for the same reasons we're talking about, right? This sort of hypermethylation. But SAMe is powerful. I mean, it's end stage for the methylation pathway. To be very specific here about sort of pros and cons, uh, when we're talking about just knowing a single gene, MTHFR, and what it's doing, a mistake is often made out there, which is just, with the two alleles, 31 and 33, and the variations that are maybe considered suboptimal, throwing a methylated, whether it's methylfolate, methyl tetrahydrofolate, quadrifolate, SAMe, TMG, you throw all this stuff at it. If SHMT1, your first runner in this relay race, is problematic, and for that matter, downstream, there are issues to consider, and the potential for this inflammation to persist. So it's folinic acid bypasses the MTHFR enzyme. That's it. Step. So that doesn't flood the system with methyl donors. The cons are in slower methylation support, and again, it's not considering for SHMT1. So folinic acid requires additional steps to convert to methylfolate, so it might be a little less effective. It's not ideal for severe MTHFR deficiency, for which, of course, there are no issues with SHMT1. That's the point of testing. Having said all that, it's knowing your entire pathway. Then we have a question from Connie. I've received conflicting information about supplements, MTHFRs. Oh, she's giving us sort of the rundown of her variations. Okay, so MTHFR CT, SHMT1AG. Okay, there's the A. MTRR-GG, fucosyltransferase GG. Geez, and then MTHFR-AC, all suboptimal on the DNA. Okay, so do I or do I not take methylated vitamins? You want to have first crack at that? I mean, it's the yes, but it's the right kinds. Once again, it's what we're talking about. If you decide to, you start slow, go low and slow, and when it comes to B12 as it relates to the fucosyltransferase, this is an instance, again, one that ghost runner. You might want to support it with sublingual B12, and the MTHFR. I'm just trying to read through this, SHMT1. So this is where you want to maybe consider folinic acid, right? That's the idea. and then monitor your homocysteine levels. And this is what we would do in a nutshell.
Yeah, and I've found that folinic acid is actually pretty difficult to find out there. So there's a brand that we have no affiliation with, but that I've recommended just because it comes in a lozenge, and it's for whatever reason it's one of the more rare ones to find out there. So there's a brand called Seeking Health that makes this lozenge that's folinic acid, and that's one of the harder ingredients to find. So that's the one that I would recommend. I've used it myself, and in the event that you have difficulty, jurisdiction by jurisdiction, that's what I would do. I don't see just MTR listed here, and that would be another consideration there as well when it comes to the cobalamin, the B12 side of things.
Yep. Perfect. We have another anonymous question which asks, which genes do you use to test for methylation? Of what vitamins and minerals does it test for methylation? Okay, so we want to ask this person to listen to this podcast all over again, because that's the whole topic. We're not ignoring it. It's just that we've covered all of this already. Vanessa's asking, where can I get adenylyl folate? So that's folinic acid. In supplement form, because most supplements use methyl. Yeah, you just sort of answered that question.
Yeah, by default,
it's prescriptive, by the way. It's prescriptive in Canada. And yeah, it's not the easiest to get. But if you live in Canada, I'll tell you what some of my patients do is actually go on Amazon.com and they order through either, you pull up, what's that called? When you're blocking the incognito, when you're blocking your server from sort of knowing what address you're using, going incognito, and you go to Amazon.com, and obviously just for your personal use, not for resale, they'll let folinic acid into the country as non-prescription. But talk to your doctor, pharmacist before starting anything. We're not, prescribing this, and you should actually, consider. Why don't you tell people about, how easy it is to actually become a client under the DNA company, and you're a part of the clinician team to go through stuff like this, because it's very important. This is not so. We're making it simple tonight, but it's a complicated, consideration of a whole bunch of genes, even outside of the methylation pathway.
It is complicated, and it's honestly 90% of these questions. Part of my answer is going to be you should probably enroll in some level of coaching, because it's a conversation that I like to also incorporate, like what's your diet like, what's your lifestyle like. I want to figure out what's disrupting methylation in your lifestyle, and I want to see how many animal foods are you getting, right? Are you vegan? Because if so, yeah, the B12 and stuff, you're not getting even dietary sources of it, right? So that's going to influence the conversation regarding supplements. Any of our programs at the DNAcompany.com, you can request me, or whoever you want to work with, but I'm one of our primary internal clinicians. So, I mean, you can always just say, I want to have a discussion with Justin about this, and then we can go as deep as humanly possible. This format isn't perfect for a lot of the type of questions of going through the entire DNA 360, however.
Justin, I said I wasn't going to do it. I might do it. We have a question from, and I just lost my question panel. Where'd my question panel go? We have a question. Where'd it go? I have too many screens open here. We have a question from, and it was asking about priority. Can you pull that next question up? Because I don't know what's happening to my Q&A here. Oh, here it is. We have a question from Echo Lee. Do we understand the interactions and priority system behind the many genes that regulate methylation? Okay, so I said I wasn't going to do it, but I think I should do it. What do you think? Should I pull up the pathway just to
pull
show
up the pathway, Bryce? It's the only way.
All right, guys, in the back end, allow me to share. You know what? So it's complicated, but at the DNA company, we're making it simple. And that's why we're talking about, the relay race. And we're talking about, one to that. And we're not pretending that it's not complicated. And we're not testing for every single gene, because you can't do something about every single gene. But epigenetically, you can up or down regulate the genes that we are looking at. So I'm going to share this, which is a depiction of the methylation cycle. I mean, again, it's limited. This is not transsulfuration. This is just methylation. So what I've done here for all the clinicians in the room, or the people like Ecoli asking the question around interactions, priority systems behind the many genes that regulate methylation, is we start the story over here, right, with SHMT1. And SHMT1 and the gene that's regulated to pass off the CH3 group here into MTHFR and then MTR into MTRR. This cycle right here and the right kinds of B12 and folic acid, reduced or not, is exactly what's going to prime. This is the relay race right here that's going to prime the rest of this cycle. Some other companies, they test for these. AHCY. We're actually, you know what? We are bringing this into the lineup next year or into the new year because, and I coded this here as orange, if you can see that. The rest of these are red. They're key as part of the cycle. And this is orange because, you know, it's somewhat key. It gives us some insights into niacin and some of the support. But yeah, we can prioritize. And the priority is SHMT1 into MTHFR, into MTR, into MTRR. And guess what? Down here, let's imagine there's a gut. And let's imagine that gut is either good or not so good at absorbing this guy right here, B12. Fucosyltransferase is the gene. Got to add that to this, by the way, this little depiction. And if there's problems there with fucosyltransferase, we're going to have to do this B12 upregulation by sublingual or injection methods to complete this. So anyway, I don't want to, you know, belabor the point, but yeah, at the DNA company, thank you for the question. We do know. And also the follow-up question by the same person was, you saying that slow COMT is associated with higher stress tolerance? Well, actually we are. Justin, why don't you unpack that a bit?
So, like I mentioned, COMT methylates and then clears neurotransmitters, right? So, when you have a slower COMT or a faster COMT, it's going to influence the rate at which things like noradrenaline get cleared, right? And noradrenaline is associated with fear, anxiety-based emotions. When something comes up and it causes you those emotions, COMT is what methylates and then clears that noradrenaline. So, slow COMT is actually going to prolong the amount of time that the noradrenaline sticks around, right? So it's actually the opposite. I would say fast COMT and fast clearance is associated with a better stress tolerance because it means that the noradrenaline clears quicker. So you'll still feel it. And there's a
stress tolerance. Yes, thank you for yes, you caught that. I didn't.
Yeah.
Stress tolerance. Yes,
Yeah.
slow COMT. So catecholamines are sticking around. Adrenaline is sticking around.
Yeah.
Yes.
Yeah, because it's higher tolerance, right? So we're talking about that. So it's actually the opposite. If you have a slow COMT, it's actually going to make it so that you don't tolerate the stress as well because it sticks around and it doesn't leave you. There is that second mover to consider, though, being the ADRA2B noradrenaline receptor. If you have a slow COMT as well as deletions, right? We measure that with indels and deletions. If there's Ds there, then it's sticking around for a long time and your body can't process the noradrenaline very well. So that's a real profile for lower stress tolerance.
And I think it's an opportunity to sort of have a quick discussion around how we never look at a single gene and make any conclusions. So within the mood, behavior, executive function, and stress, you know, stress tolerance, we're considering the ADRA2B gene, which has every relevance around adrenaline, metabolization and speed, dopamine, the DRD2 gene. We're looking at the TPH2, the tryptophan hydroxylase. We're looking at 5-HTT-LPR, serotonin in effect going home, BDNF. You can't look at a single gene to determine, you know, stress tolerance. You have to look at the whole pathway or the whole, you know, multitude of both, by the way, not just SNPs, but inserts, deletions, and of course, in some instances, copy number variations. So that's what we do at the DNA company. We have a question by Selena who's asking about autoimmune conditions. So, and the TT, particularly the TT variant on the MTHFR gene, or in general, like poor methylation in general. You know, I would say, and again, considering the whole pathway, if the pathway is inefficient or suboptimal and there is an effect, inflammation brewing without satisfying it with the right types of either methylated B vitamins or methyl donors or sulfur donors for transsulfuration or antioxidants, if you're building up inflammation systemically, you can't manage your cytokine profile, which are the hormones that basically balance a healthy, balanced immune response. So in effect, signaling agents to your immune system are constantly being told attack. And there's a, a viral theory to this. There's a whole bunch of theories, toxin theory, but usually it's a multitude of factors that accumulate and ultimately cause some discombobulation or information to the immune system to act when it shouldn't be acting. So if the whole cycle, if the methylation cycle, proves inefficient and or suboptimal, it plays a huge role in the development and the progression of autoimmune disorders. Um, Anything to add? I mean, there's immune dysregulation that increases inflammation, that allows homocysteine and toxins to build up, et cetera. So anything to add to that, Justin?
Yeah, I mean, autoimmunity is so complicated because your body just recognizes things as enemies and it just kicks on the response over and over again. I think that the methylation cycle certainly has some relevance there. I would also point you toward your glutathione genes. If you have had the DNA 360 done with us, there's one called GSTM1. And there's an interesting nuance there. If you have two copies of GSTM1, which is actually considered the full version of the gene, it actually can represent an over-aggressive glutathione profile at the level of the gut microbiome. And we do see, clinically correlating it with symptomology, people who have, Hashimoto's or rheumatoid or eczema, these things that are autoimmune. A lot of the time, I see people who have two copies of that GSTM1 because I think that your body recognizes things as enemies at the level of the gut, and it tends to wear away that gut wall. And, it can cause things like leaky gut. And we see that there's a connection point there as well with autoimmunity. So again, zooming out, the whole DNA 360 can give us more clues and indicators about autoimmunity. So have a look there as well.
Absolutely. I love Corey saying, I love your clinician report. We're getting a lot of comments and kudos about that. Thank you. We're getting better and better at the simplicity factor and, of course, the actionable component. Why don't you speak to that outside of our methylation pathway report? In understanding chronic disease and inflammation and the underpinnings of it, we do a really good job at siloing, right? Or like reports within reports for folks to understand. And you're an amazing clinician to help pick all that apart, dismantle it, and give ultimately actionable remedy, diet, lifestyle, supplementation to folks to help manage genetic aptitude.
Yeah, like I've brought up this concept in previous webinars about the butterfly effect, right? We talked about that Ashton Kutcher movie in one of ours. And, I said that different systems in the body have trickle down effects into other systems. I think that they all play into the next one. So the genes that we arrived at, listen, there is way, way, way more SNPs in the world than we actually landed on and chose for the DNA 360. What they landed on for our reports was clinically relevant, that's divided up into 6 different systems. So, this is what the nutrition looks like. This is what detox looks like. This is what steroidogenesis looks like, etc. The clinician report is great because it's an add-on that's more in depth than your traditional report would be, right? We're able to use different types of language and get a little bit more into the weeds with it. But it gives you so much detail about all of these different systems, which all matter for the next system, right? You can't just nail down glutathionization and then say, methylation doesn't matter because my glutathione profile is perfect now, right? The relevance is always there with all of it. So I'm glad that you love it. I love it too. And keep on learning because this is a process for all of us.
Absolutely. Optimal SHMT1 gene. So, the SHMT1 variant, the way we look at it, and again, and this is by Lisa Huffman who's asking, whenever there is an A, even worse if there's a homozygote, which means double A variant, poor methylation, it starts right there out of the gate, as we're talking about in that sort of dropping of the baton. So, we're gonna want to be starting to consider the type of folic acid. There are reduced forms, there are, downstream. So there's folic acid, there's methyl tetrahydrofolate or quadrahydrofolate. There's, this is all B9, by the way. Then there's adenylyl folate or folinic acid or leucovorin, otherwise known as. So these are where, if you've got certainly a homozygote A, that you're going to want to be considering something that doesn't ultimately just add fuel to the fire. Dirk is asking, doesn't B12 come from bacteria in the soil, which means primitives got B12 from root crops or any food containing soil, not just animal sources? So, do you want to start with that? That's theoretical, and I would say, there is some truth to that. It is produced by soil bacteria, um, but no, in ancestral diets, B12 wasn't just from animal sources. It was probably a combination of soil contact. Um, Today, we just don't have, it's not advisable to be eating soil. Okay. We use a sort of playful analogy, play in the dirt, grow your immune system. But you're not going to get any, significant amount of B12 in your diet by eating dirt, right? I mean, correct me if I'm wrong. This is, this is really from meat is where we're going to get, or supplementing. There's nothing wrong with being, well, there's some things that might go wrong if you're vegan, depending on your genes, but I'm not asking anyone to stop being vegan or vegetarian. Just consider supplementation based on your DNA.
Yeah, I think it would represent a certain percentage of the intake. I really think that our ancestors would have prioritized animal foods. I mean, you see even modern day hunter gatherers like the Hadza, for example. They went and they asked them, "What was the greatest day of your life?" And he said, "The day that I killed the boar. I fed the whole tribe for like a month." You know, that's the predominant. That's where all of our calories came from. That's bioavailable protein, bioavailable iron, and these different things that are really difficult to get from the soil. You could get it, but I think that it represented a pretty small amount, and animal foods would have been prized. Eggs have a lot of B12 and red meat and things. So I think you're right, Dirk. I mean, I do think that, it represented some of it, but I don't think it was notable enough. And modern context, to Bryce's point, we're not going to get workable clinical levels in our blood by having a handful of dirt from the garden.
Let's stick on that point for a quick second because we're often talking about this. Part of this concept is understanding your DNA so you know what type, format, and frankly, even dose of certain ingredients you need to add in a therapeutic range that you can't otherwise eat in your diet to therapeutic levels in order to have therapeutic outcomes. This is the point. There are health seekers, people that look to solve health problems, often tied up within their genetic aptitude, right? And then solving methylation is probably going to solve half of what ails you, is arguable. And then there are wellness seekers, people that are looking to go from good to better. And we often see one of the things that I see often with my own patient based in clinical practice, when I solve for methylation, people come to me and say, like, I haven't felt so good and so high in energy for so long. And what I tell them is basically all we've done is optimized your sort of energy pathway. You've gone from problematic within your ability to manage that pathway to normal. We haven't done anything special here. We've just accentuated or turned up the dial on your genetic aptitude to be able to do what otherwise normal people do. So, and yes, supplementation is that ability you can't get from an otherwise balanced diet. You just can't eat yourself to therapeutic range. um Question is, the next one from Echo Lee. I hope I'm pronouncing that properly. Do you ever recommend hydroxycobalamin? I mean, I do sometimes. Adenosine hydroxy combined. That it's another versatile non-methylated B12. It's again sensitive for those who have sensitivity to hypermethylation or methyl donors. So especially those that are compromised detoxifiers or sublingual. So often it's in combination with products out there, right? So there's adenosine hydroxy combined in a lot of products. So I like that because you know kind of just sort of covers all bases if you don't otherwise know. But the point is if you're, a fecal transferase compromised and maybe MTR is not optimal, sublingual hydroxyadenosine B12 is one of the better ones I like to recommend.
Yeah, agreed. I don't have a problem with hydroxycobalamin. It's usually coming from a fairly natural form, and again, cyanocobalamin is the only one that I've seen red flags from, and I think that it's great. It's non-methylated. You can use it.
Right. Nicole's asking, how does the methylation process affect hormones like estrogen in women? How do you know if you are over supplementing methyl donors? If you want to go.
Yeah, so this is definitely one of those areas where, keeping an eye on your homocysteine levels is going to be the downstream effect of overdoing methyl donors, right? Because it's going to imbalance the pathway. It can affect you in other ways, right? You can end up with panic disorders and different things if you're over methylating and over contributing. But yeah, I mean, estrogen needs to be methylated. It's one of the things that it does. So methylation is really important to get right, because once again, if you're over methylating hormones and their requisite metabolites, you're adding to the totality of the inflammation load in your body, right? That's what we talk about with 4 and 16 alpha hydroxy estrogen. It's inflammation, right? And toxicity. That's one of the broader problems. So that's where that kind of stems from. I would also look at the rest of your profile as far as like considering the totality of your inflammation, right? Like, are you also suboptimal for these other detox pathways? Because your body has a total load that it has to deal with. And toxic estrogen metabolites can be fuel to that particular fire. So a coaching program or, a conversation like that may be in your interest as well to get to the bottom of these things.
Yep. I fully agree. Okay. Nicole is, or actually, sorry, Lisa's first asking if having a GGSHMT1, is there any direction for this? If G is, no, G is that is the desirable. This can get, these SNP letters, the alleles as they're referred to, can get confusing. The MTR, let's call it the anchor in the race. If there's a G in there, then we want to address that. With SHMT1, if there's an A in there, then we want to address that. So let's be clear. SHMT1 with A or AA homozygote, you want to be thinking adenosyl folate or folinic acid. If the MTR has a G in there, the anchor, you want to be considering, a variation on your B12. In other words, adenosylcobalamin, especially if there's a fecal transferase issue that brings B12 from the diet in the gut into general circulation to the cytoplasm in your cells. Then you're going to be wanting to require a different pathway of delivery, so sublingual or injection. So I hope that helps. And then we have Nicole asking how methylation affects Hashimoto's thyroiditis. Well, by the way, are you seeing more of this? I'm seeing more of this. I'm seeing a lot more of female, patients in their early 20s with autoimmune thyroid disease. Um, and about molecular mimicry. One of the causes, obviously, I believe, and we know, is the underpinning of this starting the gut, hyperpermeability, gluten, casein from dairy, from wheat, respectively, triggering an inflammatory response. This molecular mimicry I'm describing is, if you look this up, it's black and white. It's so easy to see. The biochemistry of the shape, if you will, of gluten or the shape of casein is so closely resembling your own thyroid tissue that there is this theory that when you translocate these ingredients through from your gut into your general circulation, your immune system doesn't know what to do with this and makes these antibodies, antigens against these molecules, and then starts to attack your own thyroid tissue. Anyway, that's one driving factor. But understanding to Nicole's question, how methylation affects autoimmunity. I mean, we're talking about inflammation here. It's loosely when you're not winning the race, or when the baton, the CH3 group, is dropped in this analogy of the relay race, there's inflammation that builds up. So for individuals with Hashimoto's thyroiditis, there is an underpinning of poor methylation variation within the genetic aptitude. Would you agree?
I would agree. And I also think that the thyroid can be impacted by a lot of different factors as well, like
Of course, yeah.
conversion factors and binding globulin factors. The liver plays a role with your thyroid. The gut plays a role with your thyroid. HPA axis plays a role with your thyroid. But, I certainly see a predominance of it, like you mentioned. I think that, eczema, all these different things that are autoimmune related, I'm seeing it more and more and more. I would definitely recommend, possibly doing our gut 360 as well to see if there's too many proteobacteria in there. And that's an indicator, right, of dysbiosis in the gut. You might have to just shore up that gut wall and start working on different strategies for detoxification, etc. Again, a coaching program is what I would recommend if you want to go further on that.
Yep. Here's a little bit of other free advice. Gut rehabilitation, whether you know it or not, there's probably hyperpermeability when there's Hashimoto's or autoimmune thyroiditis. And so one thing, I mean, this is not the complete protocol, obviously, seeing as Justin's describing a clinician who knows how to tease apart all the nuance of your genomic susceptibilities. But gut rehab includes, at least in my clinical practice, and I know it's quite popular, mucilages. And glutamine as an amino acid. Mucilages are a group of botanical extracts that basically give the gut lining some refuge, some time to heal, and also allow the microbiome to perpetuate favorably, the probiotic commensal bacteria to populate effectively interlumen or intervilli. So these are, licorice extract, marshmallow root, slippery elm, that varietal of mucilages, and the amino acid glutamine helps to revitalize the microvilli where a lot of this damage is happening. Candace, let's get to your question. Candace asks, if I had a DNA 360 test done 2 to 3 years ago and I've made she has made significant changes in her diet, labs look great overall. Homocysteine is normalized. Good for you. Is a new DNA test suggested? I wasn't able to afford counseling, but might now, but couldn't do new testing plus counseling. Okay. So, first of all, DNA never changes. Science around DNA changes. We're always at the DNA company adding additional tests and new DNA to our lineup. We don't store, of course, or ever sell your DNA. So in order to get the updated reports, which you would be in time for, you do have to repeat that testing, but not because your DNA would have changed. We would have added more genes and, of course, more information around those genes to the updated testing. We're always adding programs, affordable programs to the list as well. TheDNAcompany.com will tell you all about what those programs are, and they start very reasonably. We like to talk about how your health's an investment, never an expense. I'm hoping that you are able to afford some counseling. I would actually ask a clinician first before you even need whether you need to retest yourself. I mean, the other thing I would recommend, by the way, is just email. Our CEO is one of those CEOs that has the, I don't know how she has the ability. She has the ability to be reached directly, and makes the point of being able to be accessible to individuals such as yourself that need some kind of customization around having had your testing, interested in our clinical services, but need some, opportunity here to make it reasonable for you. So Candace, just reach out to our CEO and just put your comment here actually in the webinar chat. And we'll have Tracy reach out to you directly. How does that sound? Dirk asks, can you recommend any textbooks that provide a comprehensive and detailed presentation of methylation at the level of which detail you can covered here? Well, we're trying to make it simple, Dirk. So taking this complex idea and turning it into a relay race, and specifically how we interpret it is really our IP. Is there a textbook out there? I don't know.
DNA University is where I would
Yes.
go, frankly. That's Dr. Laura Varden is one of our brilliant clinicians.
We're not kidding here, Dirk. We're not kidding. We have a DNA University, which you can study at.
Yeah, you'll learn so much about friggin' methylation and functional genomics. It'll just make your head spin. That's where I learned most of my stuff, frankly. I mean, you pick up these little nuanced, tidbitty things on health as you go, various certifications that you and I both have. But goodness, I mean, through the lens of functional genomics, it makes it so much more detailed that I would just suggest doing that, honestly. If you want to learn about just the methylation process on its own, there's plenty of good clinicians in that you can follow on YouTube or whatever. But DNAU is where it's at because it's through the looking glass of what we're really talking about.
Yep. Candace, I'm sending this to the wrong group here. Email our CEO at CEO at thednacompany.com. And yes, Dirk, good luck with the continuing education. Methylation is one of the most, intricate and most important pathways dictated by our genes that we could ever try to describe. Jen is asking, this is a nice sort of summary point. How do you know if you're out of balance with methylation, Justin?
The main point would be what we talked about earlier, as far as the homocysteine levels, and it's not just that though. I think the methionine levels as well is a good thing to look at, right? Because you want something of a balance there. A functional med person is going to have a good interpretation of what that should look like. There's also going to be other symptoms, right? If you're under methylating or over methylating, like I mentioned with neurotransmitters, an overmethylator is probably going to have some insomnia. You're going to be, more panicked, more prone to anxiety. There's a lot to that, so don't place it all on the methylation cycle. But it can be indicative. And if you're an undermethylator, right, then that's going to be the opposite: more depressive tendencies, brain fog, low energy, etc. But blood work doesn't lie. So, we have the capacity to look and see nowadays, and that's what I would do. Do you have anything to add to that one, Bryce?
Well, yeah, and I keep referring to homocysteine as a surrogate marker. It's pretty direct. There are, some really wonderful tests out there above and beyond what we do at the DNA company that look at homocysteine and even look at generalized inflammation, which are surrogate markers. I mean, indirect. You want to control for homocysteine, excess homocysteine. The glycomark, which is sort of a more sensitized insulin marker, C-reactive protein, high specificity, 11-dehydrothromboxane, a number of, surrogates to homocysteine and inflammation. So I think that's important, whether that we're talking about heart disease, psychiatric DSM schedule and or mood behavior issues that are non-diagnosable, through to the big C, right? Cancer predisposition, which, by the way, we also offer a liquid biopsy at the DNA company, and that's worth, every penny by being able to predict. It's not diagnostic, but high, level prediction of over, 50 different types of cancer out there that are brewing, or at least that suggest that you might want to flag and, do some further due diligence with your healthcare provider when risk analyses show positive. All right, where are we? You actually answered the question from Deborah. Can we overdo foods in an indirect way? Do you want to extend what you just said to, foods? And can you overdo foods? Again, sort of in the theme of not really being able to, consume foods at a point where you're going to get to that therapeutic level that supplements do, or that a B complex would at the right form, obviously.
Yeah, I think that you would be overdoing calories were you to actually get to that point, and that's a much bigger problem, most likely, right? Just an overabundance of energy input. The only time that I've seen any kind of problem with that would be people who did like a carnivore diet and they didn't do it in a well-rounded manner. Like if they ate a lot of just muscle meat that's really methionine rich and they didn't balance it out with some sort of glycine source, right? Like there's glycine in the organs, there's glycine in the skin, like collagen has some glycine in there. There's a delicate amino acid balance. And that's why when you hear people on these animal-based diets referring to nose to tail, I think that balances it out quite a bit. But if you eat only muscle meat and it's independent of the rest of the animal, you can definitely mess the system up a little bit because it's so methionine heavy. But yeah, you're talking about the difference between that and supplementing is astronomical, right? An isolated nutrient you can overdo way easier, and I wouldn't worry about it too much with the diet.
Then we've got a question from Jay Francis. What does methylation process look like when you've got indoor and outdoor allergies, as well as polycystic ovarian syndrome and autoimmunity? Yeah, chronic. So the hormone methylation pathway together and separately is going to identify issues this way, and then add to that the glutathionization detox pathway. And my friend, we would be able to personalize a protocol that is life changing for you. So, in summary, efficient methylation is crucial for managing what we covered it: chronic inflammation, hormone balance, and immune regulation, right? And when that's not managed properly, you get things like cardiovascular disease, hormone dysregulation, autoimmunity, anything with itis at the end of it, by the way, as well. And by the way, this makes me think about histamine levels, some other things, probably another webinar altogether. But by supporting methylation with the right nutrients, in some instances needing maybe folinic acid, maybe needing different delivery systems of properly methylated B12. B2 is playing a huge role. Niacin, the whole B6, all these things play a role. Trimethylglycine, S-adenosylmethionine, methyl donors at the right dose, at the right amounts, in the right formats, and you can better manage symptoms related to allergies, PCOS, and autoimmunity. That's what we're getting at here. So Roberta is saying, I have digestive disorder concerns and my gene code. Whoa, we're getting like, so CYP2R1, GG, VDRCC. Okay, so there's some issues around vitamin D, MTHFR-CC, converting. Okay, so SHMT1, GG, fecal translate. So, SOD2. Are you reading this from Roberta simultaneously here? So, so we know that there's some issues obviously within there. Not all of those are issue, but some. I'm on a paleo diet, no meds, lots of supplements, just switched to liposomal B supreme. Okay, that's just a better, more absorbable form of the B group, and that's fine. Not considering obviously MTHFR, considering fecal transferase. Would love to know your thoughts for digestion, sleep, and cardio. Roberta, please book an appointment with Justin Harris. Calling Justin Harris for Roberta.
Yeah, there's a few moving parts to that, right? It's a fairly big question because we're talking about different pathways, right? With CYP2R1 and VDR, we're talking about vitamin D. You've got several methylation genes that we're talking about, and then you bring up SOD2, which would be mitochondrial. And I never talk about SOD2 without also looking at GPX because it's a very important tandem profile. I would also want to know what your GST genes are when it comes to digestion, right? Because that's an important one. Sleeping, we've got the clock gene, there's a whole profile, right? We want to look at your whole executive function profile as well. Within cardiovascular, there's 9P21. There's quite a few more. So, Roberta, I would certainly recommend booking an appointment with myself and we can go over all of the above. But there's a little bit too much to go into on that one for this particular type of context.
Yeah. Wendy's asking a great question. If she's still there, I'd like to hear from Wendy. We're coming to a close here, folks, but just if you could answer me, Wendy, on whether or not you know if your fecal transferase is problematic or not. She's taking, or if you haven't done your testing, obviously that's what my suggestion would be. But she's taking adenosine B12 from Pure Encapsulations. And her annual labs come back B12 deficient. I'm going to guess, by the way, because Pure Encapsulations make a liquid and a supplement, oral supplement. I'm going to guess that she may have issues with fecal transferase, FUT2 gene, and that she should switch to sublingual if she's already taking the sublingual. What we talked a little bit earlier about hydroxycobalamin. So here's an instance where hydroxy is a little longer lasting, by the way. So it's a more sort of stable, non-methylated form. And again, depending on all the rest of her genes, MTR, the anchor in the relay race, right? I mean, what is that doing? So, but the flexibility of hydroxycobalamin lasting longer sublingual, maybe we need an injection, maybe we need it in a higher dose, right? Most of these are 1,000 micrograms. You don't need more than 2 or 3. And most people are coming up with serological reports that say, 3-4 times the amount. Doctors are freaking out. Not sure the jury's out about that one, whether or not it's problematic, but nonetheless, it's serological, not intracellular. So a lot of things to be considered. But without knowing, Wendy, really the entire methylation pathway needs to be identified. I don't know. We've covered so much. I think what the most important thing to acknowledge, though, is that we're always doing our best at the DNA company to make methylation simple. It's a complicated concept. It's a pathway. It's very important to acknowledge and understand variations within that genetic pathway play a huge role in overall health. And if you don't know what that pathway is for you, that single-handedly, along with, I believe, hormones and detoxification, is a game changer. What are your final thoughts, Justin?
Yeah, I would consider the methylation cycle one of the more important aspects of all that, and it is one of the ways that the body deals with inflammation, and that's that word just we can't escape it. It just keeps going and going. Every time I coach someone, we end up talking about inflammatory factors because again, our ancestors had a very different world than we have now. So yeah, the methylation cycle, getting it right, it's going to impact every single system of the body. Every cell of the body is impacted by that. So getting it right matters, and get it right. That's all I can say. Get a coaching program, get your genes done, and let's get it right because you'll have a better health and lifespan if you do.
I Lifespan, health span, adding years to your life. That's what we're all about here. By the way, we don't throw this around loosely, this term, change the day you die. Knowing your methylation genes can literally change the day you die. And of course, achieving optimal health is all about tuning into your body's unique needs. Methylation, that's the B12, that's folic acid gene variants. And these aren't really details. They're the keys, the absolute bottom line keys to unlocking energy balance, immune function, and a whole host of other things. So, with the right choices, you're not just managing symptoms, you're building a foundation for vibrant, long lasting wellness, just as you said. And every small adjustment counts, right? So, listening to your body, supporting it, um, your health's an investment, not an expense. So, here's to making empowered choices and for the health and vitality that you deserve. Your health's an investment, not an expense, folks. Thanks so much for tuning into tonight's webinar. And that is it. Justin, have an amazing night, my friend.
You too, brother. Thanks
All
for
the best.
coming, everybody. Have a great
Thanks,
night.
guys. Cheers.